Good evening, everyone. My name is Mansi Tripathi. I am TA for this course, Wastewater Treatment and Recycling. So, we are entering the fourth week of our course. So, we'll be solving some of the exemplar problems from this fourth week questions. So, this fourth week was basically about self purification of the river as well as some reactor kinetics. So, what is self purification? You must, or you all of must, you have noticed, or at least you have seen the news that during the COVID times, when all the anthropogenic activities, means the human activities, were kind of closed, like there were industries were not working, and all those things, then we came to know that the rivers were restoring. It means that rivers, the water quality of the rivers was getting better day by day. How was that happening? It means this all was due to the some natural purification process. So what happens is when we put some pollutants in the river, it tries to get into the original shape. Means it tries to get better. So there are various self purification phenomena that works on that river, and it tries to restore the original state, that is the clear state. So, Sir has already explained beautifully about all these processes. So, we will try to solve some exemplar problems on that. Allow me to share my screen. So, this is a fourth week sample problems. We'll see the questions at the next. You can answer the question in the chat box, or you can use the polls that I have just launched. The question number one is transformation or degradation of the pollutants in natural water bodies may be. Here you can see the two terms, transformation and the degradation. So basically, degradation means state, the pollutant state is changing. It is changing from one form to another. And transformation means that it is transporting from one place to another, or the concentration is decreasing. So in case of natural water purification bodies, we take both the things as one. Means we consider both of the things are similar because both of the things means the concentration is decreasing. The bad concentration of the pollutant is decreasing. So try to answer this question. Transformation or degradation of pollutants in natural water bodies may be biotic, abiotic, photodegradation, or all of the above. So we'll see the answer as well as I'll launch the polls if you can see. So try to answer this question. Transformation or degradation of pollutants in natural water bodies may be biotic, abiotic, photodegradation, or all of the above. So here we need to tell what are the various phenomena by which either transformation or the degradation of the pollutant will take place. We'll see the answer now. So answer is all of the above. And in this question, I have also kept the reference from where you can see all these things in the main lectures. So you can see the slide number 2 of the lecture 16. So you will be able to find the answer of this question and the basic explanation why all these things are happening. In case of any doubt, you can ask me in between. Okay, we'll move towards question number 2. Aquatic animals are more vulnerable to lower DO in evenings in winter, early mornings in hot summer, high stream flows, all of the above. So, first of all, we need to know two things very important. One is photosynthesis. photosynthesis leads to the production of DO during the daytime, and night time it takes the DO. DO means dissolved oxygen. And the another important factor is solubility of DO. So during, if the temperature is high, the DO concentration will decrease in water. If the temperature is low, the oxygen concentration will increase in water. So these two basic things, first of all, we need to understand. The DO depends upon the photosynthesis as well as solubility. So by this, you can try to answer this question. So first of all, uh, aquatic animals are more vulnerable. Means here DO is decreasing. So what are the two factors by which DO will decrease? First, temperature is high. Second, photosynthesis is not there or less. So looking at the things, option number A, evenings in winter. First of all, it is winter, so temperature will be low. So there will be not much problem related to DO if other factors are constant. And evenings, evening means whole day it was daytime, sun was there, means photosynthesis was happening, means DO was increasing. So here whole day DO was increasing as well as temperature was also less. So both the conditions are in favorable, means there will be good amount of dissolved oxygen in water. Coming to option B, early mornings. What happens before early morning? Night. When there is night time, DO is consumed. DO decreases. One problem. Second is hot summer. So when temperature is high, DO decreases. Means both the condition are saying that the DO will decrease. So DO will decrease. And option C, high stream flow. So DO does not depends upon high stream flow. Like if some water is coming with lots of DO, it will increase the DO. If some water is coming with less DO, it will decrease the DO. So it's not a important factor. Either high stream or low stream, anything can happen. So A and B were the correct options from which we have to choose the which will reduce the DO. So by this explanation we can see that option B is correct. So early mornings in the hot summer. DO is lowest in the early morning as no oxygen was produced after the sunset. Means at night time no oxygen was produced and even the temperature is high, so DO was decreasing because it won't be more soluble in water at that time. Moving towards question number 3. Very less life forms exist in. Here these are different zones in the river during the self purification. So we need to tell when with the life form will be the least. So it depends upon the DO. In septic zone, DO will be very less. I'm giving you all some hint. In recovery zone, DO will be little bit increasing. When decomposition starts, DO will be consumed. And reaeration zone, reaeration means more air will come, so DO will increase. So between these two terms, 1 and 3, in which zone DO will be the least? That will be your answer. DO means dissolved oxygen, okay? So we'll see the answer. Answer is septic zone. Because in septic zone, oxygen, amount of oxygen is very less. This is 40% oxygen. In septic zone, it is less than 40%. This is septic zone. then it will increase to 40%, then it will go to saturation. And the reference is in slide number 12, lecture 17. Moving towards next question. Optimization and design of treatment units is based on energy balance, volume balance, mass balance, and momentum balance. So whenever we design a treatment unit, it is kind of a reactor. So what do we check in these things? Energy, do we balance energy, volume, mass, or momentum? Some compound will come in, some will go out. So in this control volume, what do we measure? This is very important question. These
Volume
things,
balance.
yes?
Volume balance.
No, no, no. We never balance volume because volume may increase or decrease with time. Okay, if you will increase the temperature, volume will increase. Okay, same thing is coming, but increasing the temperature, volume will increase. Talking about gas, it will increase tremendously. So we never balance volume. We balance mass because mass is constant. Okay, so mass balance is the answer. We try to balance the mass. Some Q is coming. Q means flow. Some concentration is coming. What is the unit of Q? Let's say meter cube per second. What is the unit of concentration? Milligram per meter cube or gram per meter cube. Okay. When we multiply this Q into C, what will be the unit? Meter cube per second into gram per meter cube. Okay. So this meter cube will be the cancel. So we will get gram per second. And we try to measure the time for which the compound will be there in this unit. We multiply it by time. What we will get? Gram. And gram is the unit of mass. So we try to balance the mass only. Okay. Any doubt? You can ask in between or you can put it in the chat box. Anything is fine. Moving towards next question. This is numerical. Try to get calculator with you so that you can solve the question. So this is saying deoxygenation at 21 degree Celsius is 0.17. So we need to find the deoxygenation at 27 degrees Celsius. Try to solve this question. And I have launched the poll. You can answer the question. Okay, we'll see the answer. So KD at 27 degrees Celsius. My pen is not working. So KD at 27 degrees Celsius is equal to KD at 21 degrees Celsius, 1.047 raised to the power. This by 6 is not written here. Shouldn't be written here. It should be like 27 minus 21. So the basic formula is kT is equal to kt naught theta raised to power t minus t naught, and theta is equal to 1.047. So this is the basic formula. This you need to learn because this will be used almost everywhere in water and wastewater treatment. Either we are talking about river, this theta will change. Theta will change with reaeration or the or anything, deoxygenation. It will change, but this basic formula will remain same. This you need to learn. So we will get the answer as 0.23. Moving to our next question. Question number 6. This is theoretical question, and I think kind of similar question is given in the fourth week assignment as well. So a steady state in a reactor indicates that no reaction is occurring inside the reactor. The concentration are same everywhere inside the reactor. The concentration in the influent and effluent are not changing with respect to time, and all of the above. So there are three basic concepts that we need to understand. One is steady state and other is uniform. Steady or unsteady. Second is uniform or non-uniform. With every question, I'll try to give you a brief concept. So it will be good if you try to understand this. When we talk about steady and unsteady, what we consider is time. And when we talk about uniform and non-uniform, what we consider is space. Space means x direction, y direction, z direction, and time means t. So here first of all we are talking about, could you please mute yourself, Subhash? Thank you. So we are talking about space when we are saying uniform and non-uniform, and we are talking about time when we are saying steady and unsteady. So you can see the solution. Since we are talking about steady state, it means we are talking about time, and steady means the concentration is steady. It's not changing with respect to time. So C is the correct option. Moving towards next question. A continuous flow reactor usually operates in, so here we need to answer it. Does it operates in steady state, transient condition, both A and B, or none of the above? So what is continuous flow reactor? First of all, there is two words. There are two words, continuous, second is flow. If this is a reactor, two things are happening. Flow is coming in, flow is going out because flow reactor. Now it's continuous. Means flow is continuously coming in, continuously going out. It's not like intermittent, like we are putting some flow, then we are waiting, then we are taking the flow out. No, the volume remains constant because the speed of by which flow is coming in and flow by which coming going out is same. So the volume is same. Answer this question. Steady state condition in long term, transient condition after startup and before attaining equilibrium, both A and B are correct. Let's look at the answer. So answer is both A and B are correct. So what will happen? See, when like just imagine volume is 100 meter cube and the concentration is 5 milligram per liter. Here the volume coming is 2 meter cube per second and the concentration is 20 milligrams per liter. And just imagine here the things are remaining for 10 seconds. In 10 seconds things are going in and coming out. So let's see why what is happening here. So when this 2 milligram per liter 2 meter cube per second is getting inside this 100 meter cube material, what is happening? The concentration is suddenly lowering. How? The concentration, just immediate concentration can be 2 meter cube per second multiplied by 20 milligrams per liter plus this 100 meter cube. Since this is in meter cube per second, so we will put this is also in second multiplied by 5 divided by the flow 2 plus 100 by 10. The concentration which we will get will be between 20 milligrams per liter and 5 milligrams per liter. So when it is starting up, there is sudden change in concentration. Okay. After that, the concentration will be similar inside the volume. Means A will happen, steady state condition. So initially there will be transition just at the instant when we are putting our contaminant in this reactor. It is in it is in an unsteady state, means transient state, and after that it will attain steady state. Okay, so that is how it is happening. So that is why both A and B are correct. So this is question number 8, and these are the polls for question number 8 as well. Which of the following statements are false about plug flow reactor? False. Okay. The content remains completely mixed. What is plug flow reactor? Plug flow reactor means there is a reactor which has good length but very less width. Means length is so much greater than width. Then only it's plug flow reactor. It's like a river. So the content remains completely mixed. Fluid is mixed in the radial direction. There is negligible longitudinal mixing, or example include pipe flow. So content remains. So the main thing, the main difference between continuous flow reactor as and plug flow reactor is this point. In the continuous flow reactor that I have explained in the previous question, there all the contaminants were completely mixed. But here in plug flow, the concentration here and here will be different. Here it is C1, so here it will be C2. But the concentration in this line will be same. Everything will be C1, C1, C1. Okay, so this is the major difference. Okay, in the same cross section, concentration will be same, but in the different cross section, concentration will be different at the same time. So that is why option A is correct. Means it is false about this statement. Moving towards next question. The mass balance equation for a completely mixed reactor with first order decay is given by, you have to tell this question. This is a reactor. Here Q is going in and concentration is C in. Here the Q is coming out and the concentration is C. inside volume is V, concentration is C, because this is completely mixed reactor. It means the concentration going out and the concentration inside the reactor will be same. Now it is saying first order decay, means the reaction which is happening inside is in first order. First order means dC by dt is equal to Kc, means the indices of this C is 1, power is 1. So we can answer this question. So mass balance is important here. Volume dC by dt is equal to Qc in minus Qc out, because this flow is coming in, this flow is going out, plus minus dC by dt volume reaction. So reaction, it is saying it is first order decay. So dC by dt is equal to Kc. What we will get? Qc in minus Qc out, minus, because when the reaction will happen, the concentration will decrease. That is why minus. Otherwise, if the concentration is increasing, we will put plus. If the concentration is decreasing, we are putting minus. And what is dC by dt? Volume will be there as it is. dC by dt is Kc. See, the thing is, the concentration inside the reactor and the concentration going outside the reactor should be same. So I have kept, here I have kept C and here I have written C out. So C out and these things will be same. So you can see the answer now. What will be the answer? So answer is first one. I'll clear it so that you can see. Okay, first one. The concentration inside the reactor as well as the concentration moving outside should be the same. That is the most important criteria that you should understand. And those who have answered D, see here everything is right. Everything is right. But this is the problem. Here it is saying the concentration going outside and the concentration inside the reactor is different. So that is not the case here. Always in completely mixed, going inside, going outside, and the concentration inside the reactor is same. Okay, I hope you understood this concept. Moving towards next question, since we were solving the questions related to completely mixed tank reactor, so this is the question related to the same. We will try to solve this question. Please note down the values. I will solve this with you. Volume is equal to 500 meter cube. Okay, we will draw the diagram and solve. Always draw the diagram and solve. It will give you the complete picture. Volume is 500 meter cube. Water from singlet inlet. So water is coming, means Q in is 40 meter cube per hour and containing how much contaminant? 30 mg per liter. And take care of the units as well. So we need to tell steady state TPH concentration, means we need to tell C here as well as C going out, because as we know these two C will be same. So same C I have written here in both the places. And what will be the Q? Same Q which is coming in will go out. And this is saying first order kinetics. Same equation will be there. V dC by dt is equal to Q in C in. Okay, I will write so that will be easy for you to understand. Easier for you to understand. Q out C out minus KCV. Now, this is the basic question. Now, what do we need to see? First of all, it is saying that we need to determine steady state. When we are talking about steady state, dc by dt, anything related to time will be 0 because there is no change with respect to time. So, this is 0. Rest of the things we know. How much is Q in? 40 meter cube per hour. How much is C in? 30 milligram per liter. How much is Q out? 40 meter cube per hour. C out we need to find out, and KCV is 0.25 per hour. See, if this KCV is if this K is given in terms of per day, then we need to change this. Either we need to change this in hour, or we need to change this meter cube per hour into meter cube per day. Then only solve. All the units should be similar. K, C we need to know. Volume is 500. Okay. Solving, this is 1200 minus 40C. Okay. And if this is equal to 0. Volume is also there. Volume multiplied by 0, we will get 0 only, right? So 1200 divided by 125 plus 40 is equal to C. What do we get? We are getting 7.27 mg per liter. All of you are getting my point? You got this answer? If there is any change, you can tell me. Because I am solving with you both, with you all. Okay, I'll clear the screen and we'll see the answer. So yes, answer was correct. 7.27 milligram per liter. Thank you, Shekhar. Okay. So we'll see the next question, question number 11. Here the same thing is, with respect to previous question, what should be the approximate volume of the corresponding plug flow channel if the same degree of pollutant reduction is needed? Okay, with unchanged flow rate and Q. Now we need to know the volume of plug flow reactor. Here we are talking about plug flow reactor. Try to solve this question. I'll show you the previous question so that you can get the volume, you can get the flow rate as well as the value of K. Flow rate is 40 meter cube per hour and the K is 0.25 per hour. We need to find the volume. Here volume was given and we need to find the volume. So first of all we need to know the degree of treatment. Initial concentration was 30 milligram per liter. What is the final concentration? 7.27 milligram per liter. So what is the degree of treatment? How much treatment we got? Efficiency? C not. This is not required. This step is not required. I am just showing you how to calculate the efficiency. 30 minus 7.27 divided by 30. into 100. This step is not required. I'm just showing you how much we have cleaned. 75.8% almost. So how much treatment is needed in the next question is 75.8%. Treatment is needed. C naught 30 mg per liter. C is 7.27 mg per liter. Flow rate is, what was the flow rate? 40 meter cube per hour. 40 meter cube per hour as K was 0.25 per hour. What will be the volume of the plug flow reactor? We'll see the solution. So in the plug flow reactor, mass balance equation is this: QC in, QC out, QC in, QC out, and volume K and C. Okay, here QC out and the volume inside the reactor will be different. Okay, you can see C out and C, because what I told you, at every position concentration will change. So concentration will be different here and here. You can see the solution. QC in is minus QC out minus KCV, and QC out is QC in into A raised to power KV by Q. Solving this equation, we will get this. So ln C out C in KV by Q, and when we will solve it, we know the C out, so we will get this 113 meter cube per second. I will share this PDF with you so that you can solve it in your own speed and check if the answers are right or not. If there is any discrepancy, you please let me know. We'll see. So this is the next question, and these are the polls for question number 12. The sewage of a town is to be discharged into a river stream. The quantity of sewage produced per day is 8.64 million liters, and the BOD is 450 milligrams per liter. Quantity is produced, or we will write in terms of volume because it is given in terms of volume. 8.64 sewage million liters, and BOD of sewage is 450 milligrams per liter. Discharge of the river is 300 liters per second of river, and this is in per day. Okay, discharge of river is 300 liters per second, and BOD of river is 3 milligrams per liter. See here, very important thing is unit. These two units are same, but these two units are not. So we will change this unit into liters per second. So we'll see 8.6 per million liters means 8.64 10 raised to power 6 liters, and it is in per day. So per day we will change to seconds. One day has 24 hours. 1 hour has 60 minutes, 60 seconds. So 8.64 into 10 raised to power 6 divided by 24 divided by 3600. We got 100 liters per second. Okay, so we need to find out the approximate BOD. So this is the simple dilution question. What will be the approximate BOD? 100 liters per second into 450 plus 300 liters per second into 3 divided by 100 plus 300 liters. We will get the answer from this. Answer is 114.75 mg per liter, which is approximately equal to B. We'll see the answer if it's correct or not. I'll clear the screen so that you can see it clearly. So answer is 115 milligrams per liter. Okay. We'll move towards next question. A 3-day and 5-day BOD's values of a sewage sample are 100 mg per liter and 150 mg per liter. The value of BOD rate constant. We need to find the value of BOD rate constant expressed in per day and natural log. Natural log means at the base E. Okay. So what is the value of BOD? L is equal to, let's represent it by L, 1 minus e की power minus kt. This is BOD, right? So it is saying 3-day BOD. So L 3-day BOD is equal to L naught, we don't know, 1 minus e की power minus 3t, because we don't know the 3k, we don't know the constant k. Other thing is L5 is equal to L naught 1 minus e की power minus 5k. We need to solve these two equations. This value is 100, other is 150. Solving 100 by 150 is equal to L naught cancel. Fine, right? 1 minus e की power 3k, 1 minus e की power minus 5k. Solve this question. Am I doing it right? This will we get 2 by 3, right? So you can see the answer. We will get the answer as 0.063 per day. We can check this. Okay. By solving, we can check this and we will get this answer. If there is any doubt, you are not getting the answer, you please tell me. We'll solve it again. You can try to solve this question. See if you are getting the answer. Okay. We'll move towards next question. Question number 14. And these are the polls for question number 14. This is also a numerical based question. Determine the ultimate BOD. and 1 day BOD respectively for a wastewater whose 5-day BOD is 200 milligrams per liter and the constant is 0.23. So what it's saying, we need to find, we know the L 5-day, L naught we need to find 1 minus e की power 5k. L5 is 200. L naught we need to find 1 minus e raised to power minus 5 into 0.23. We can find L naught from this, and using the same L naught we can find out L1. Shall we say 5 into 0.23? I am getting L naught as 292.6 milligrams per liter, and it is matching with this one. So we'll see this one. L1 is equal to 293, 1 minus e की power minus 1 into 0.23 is equal to 0.23. Shift e raised to power minus 0.23, 1 minus, yes, L1 I am getting as 60 mg per liter. Okay, we'll see the answer. Yes, this is the correct answer. You please try to solve it by yourself. Only then you will learn. We need to determine the 5-day BOD at 25 degrees Celsius of the same question. Here, since nothing is mentioned, so maybe the BOD is at 20 degrees Celsius. If nothing is mentioned, you can say that BOD is 20 degrees Celsius. We need to determine at 525 degrees Celsius. So what was the equation? K25 is equal to K20 1.047 T minus 20, means 25 minus 20. Okay, we will use this equation and we'll solve. Yeah, we got 0.29. Ultimate BOD won't change, ultimate BOD will remain same that we got in our previous 293. We got ultimate 0.29. 293 was ultimate. 1 minus e raised to power minus 0.29 into 5, and we need to get BOD at the fifth. What will be the answer? 0. I'm getting my answer as 224. We'll see the answer. Yeah, it's 224 milligram per liter. So in this there were so many numericals. Even this is lecture should be full of numericals. So you try to practice as much as numericals possible. Maybe Sarah suggested few books. You can download the PDF of those books and you can practice as much as you want. So this lecture will be very helpful. Whatever Sarah taught, this topic is very helpful. This is very important. All of your water and wastewater treatment will be based on this only. So what are like engineered systems? We use the natural treatment processes by these rivers. We use that process only in our wastewater or water treatment plant. Okay. So if we will understand the natural process, then only we will be able to implement all those processes in our engineered design systems. That is why we need to understand this natural process. Okay, is there any doubt? The class is about to end. It's 1 hour. So, any doubt you can ask, or you can post your doubts in the question answer forum in the NPTEL webpage. We'll try to solve all of your doubts. Okay. We'll close the session now since there is no doubt. Okay. Bye bye.